Talking about some early result in this area, which was joint with Mike Malloy. And then I'm going to talk about a recent result, which is joint with Felix Juice, Guillaume Perronel-Lobet, and Dieter Rottenbach. My paper with Mike is my most cited paper, and it's been cited more often in journals which aren't in math or computer science than journals that are. So I thought I'd start off by just giving you some examples to show you why there's such an interest in random graphs with a fixed degree sequence. So a giant component, I think you probably all know, is just a component which has a linear proportion of the vertices. Okay? Constant fraction of the vertices. So our question is going to be about whether or not there's a large component in the graph. So here's a map of a tuberculosis outbreak in Oklahoma from 2002. There's a real interest now in epidemiology. They've observed that people have different amounts of contacts, and so they may have higher or lower degree, and so that's going to affect how the outbreak spreads, and so they're interested in modeling that factor and figuring out how to deal with it. That's just a picture of the web from 1998. This is a picture of the interactive from a rat cell, the connections in the proteins. Most of the clusters correspond to cancer. And so by analyzing the structure and by figuring out ways of attacking the connectivity, hope to help cure cancer. That's just a social network. Here's an example. This is a graph in which all the degrees are 2. Okay. So that's a 2-factor. And as most of you will know, you can solve the traveling salesman problem by finding a lowest cost 2-factor and then trying to piece together the cycles in order to get a low-cost tour. So you can think of different kinds of random 2-factors. You can just take a uniformly random 2-factor where every 2-factor is equally likely. These 2-factors were generated by Bill Cook, and what he did is he put endpoints in a square uniformly at random, and then he found the cheapest 2-factor using the Euclidean distances. And he, along with some co-authors, have the fastest code to solve the TSP. He's interested in understanding these 2 factors in order to speed up the code. And if you look at these 2 factors, they all have a long cycle, which seems to have a constant proportion of the vertices. And he asked me this spring whether or not it was true that a random 2-factor of this type always has a giant cycle, a giant component. And that would differentiate it from a uniformly random 2-factor. If we just look at all of the disjoint union cycles and take one uniformly at random, then for any epsilon, the probability we have a cycle of length greater than epsilon n, component of size greater than epsilon n, will lie strictly between 2 constants, which are between 0 and 1. Okay? So you don't almost always have a giant component. You don't almost always not have a giant component. But Bill's belief is that for these Euclidean 2-factors, it's different from the random one. And if you could understand why these random ones are different from the uniformly random one, that might give you some insight into how to help find the TSP solution faster. This is a classic problem in mathematical physics. You're given some lattice, and you leave the edges in with some probability and remove them with probability p, and remove them with probability 1 minus p, and you look at the largest component that you get. Often they're talking about an infinite lattice, and they want to know whether or not there's an infinite component. Okay. And of course, when you think about all of these random models, the more edges you have, the more likely you are to have a giant component. But that's not the only thing that affects what's going on. Another thing is is what the degree distribution looks like. So these are three examples of different kind of distributions. Of course, if you have a lattice, then all the degrees are the same. This is the distribution of the number of friends people have in Facebook. And it follows what's called the power law distribution. So the probability that you have degree x is like x to the minus beta for some beta. Whereas the classical Erdős-Rényi model, or this is also the model of connections in the brain. I don't have time to explain that precisely. There, the probability you have degree x falls off like e to the minus x. Falls off much more rapidly. And it turns out that whether or not you have a giant component depends not just on the number of edges, but also on the degree distribution. And that's what I want to talk about. And those were some examples of random or models you might want to, networks you might want to take a random model of that have different degree distributions. Okay, so again, we're going to talk about a uniformly chosen graph on a given degree sequence. So I specify a degree degrees d1 to dn, and I look at a graph where vertex I has degree I, and I take each one of these graphs with the same probability, which is equally likely. And permuting the labels doesn't change the probability you have a giant component. So we'll assume that the degrees are increasing or non-decreasing. And we'll also assume they're all positive, because the vertices of degree 0, you just throw them away and look at what's left. They have no effect on the giant component. Okay. So how do we characterize if we have a giant component? Here's a heuristic argument which should give us a characterization. We just build a breadth first search tree. So we start at some vertex and we expose how many neighbors it has. And then we expose one of their neighbors and the degree of that neighbor. Right? And now we have, instead of having 3 open edges, we now have 5 open edges to explore from. So what's happening in the number of open edges? It changes. If we pick W as a neighbor, it changes by the degree of W minus 2. We lose 1 and we gain the degree of W minus 1. Right? And what's the probability we pick W? Well, every edge we should pick with the same probability, so the probability we pick W should be proportional to its degree. Should be the degree of W over the sum of the degrees. Okay. So our expected change in the number of open edges is going to be the probability we pick sum over all U, the probability we pick U times the change if we pick U, which is this. So forgetting about the normalizing denominator, you might think that what determines whether or not you have a giant component is whether or not this sum is positive. Because of course, if this sum is positive, then the positive probability in this random walk, the number of open edges will keep going up. Whereas if this sum is negative, then you expect the random walk to crash back to 0. So that's the heuristic argument. And what Mike and I did over 20 years ago was to prove this given all sorts of technical conditions. We wanted some kind of smooth sequence of degree sequences whose length was going to infinity that satisfied some smoothness conditions. And also, we said if this sum was greater than epsilon n, there is a giant component, and if this sum is negative epsilon n, then there is no giant component. And another technical condition we had to impose was that the degrees are not too high. Okay. So how do you change this heuristic argument into a proof? You've got to worry about a few things. First of all, the probability that you pick W, because we're looking here at simple graphs, so no loops and no multiple edges. Now, if we allowed loops and multiple edges, then when we go back here, the probability we pick W really would be this value. Okay? But if we don't allow loops and multiple edges, then the probability isn't necessarily that value. So if we're talking about a simple graph, this may not be right. Also, we need to make sure that the expected change stays the same throughout the process. Okay? You have the expected change at the first step, but as the process goes on, what's happening to that expected change? Thirdly, we know what the expectation of the random walk is, but we have to say that with high probability it's concentrated around its expectation. So we somehow have to connect the typical behavior of the walk to its expected behavior. Okay? And this technical condition about not having high degrees is crucial in doing that. How do you say when is a random process concentrated around its expected value? Typically when each step only makes a small change. And the change we're making here is the degree minus 2. So in order to bound the step changes, we need to bound the degrees. Okay? So that's one reason for these technical conditions. And the other reason is if the degrees are small, then the simple process is not that different from the multigraph process. Okay, so we can actually analyze the multigraph process and use the probabilities there to deduce probabilities in the simple process. Okay. And the third thing is that if these conditions hold, then the expected change does remain positive throughout the process. Okay, so that was the result, the old result, and for a long time, because as we've seen, the interest in this problem often comes from networks where the degrees are high, like have a power law distribution. We actually want to be able to handle the high degree case. So the question was, what happens when you have vertices of high degree? Why can't we prove this result when you have vertices of high degree? And the main reason you can't prove the result if you have vertices of high degree is because it's false. Okay? So think about this example. You've got all the degrees are 1, except the very last degree is some big number, bigger than, say, 2 root n plus 2. Okay? Then what's the sum of the degree of di times di minus 2? All the vertices of degree 1 give you 1 times minus 1, which is minus 1. So that sum is minus n minus 1. Okay? And the high degree vertex gives you 2 times the square root of n plus 2 times 2 squared n. It gives you a little bit more than 4n. So the total sum is 3n. It's positive. So the heuristic would say you're going to get a giant component. But of course you don't. The graph always looks like this. It's a star plus a matching. Right? So you're going to get one component of size 2 square root n plus 3, and all the others have size 2. So what went wrong was the expected change did not remain the same throughout the process. Okay? What happens is as soon as we pull the high degree vertex in, now the expected change is negative because it's not out there to be picked anymore. Okay? So if we're going to prove it for high degrees, we have to figure out what the statement is that's really correct. And even after we've done that, the other two things we have to do, we still have to worry about the fact that we're looking at simple graphs, not at the multigraph, and figure out how to deal with that probability we pick W. And also we have to worry about the concentration results because we don't have bounded step size, so we can't easily prove we're concentrated around the expected value. So let me tell you how we need to change things if we have high degree vertices. Okay? And again, in order to answer this question. So we're looking at the same question. Now we want to allow high degree vertices. Okay, and I need 4 definitions to explain this. M is the sum of the degrees in D which are not 2. Okay. And we say the degree sequence is well behaved. Basically, it means that we have the sum of the degrees which are not 2 goes to infinity with n. Okay. And now what we do is we take the value di minus 2 and we look until it's 0. And then after that, instead of summing di minus 2, we just sum the degrees. So we look at JD is the first j where this sum is greater than 0, and then the thing that we're interested in is RD, is the sum of the degrees after that. Okay? And then here's the point. The point is that this sum that we were looking at before is always at least RD. Because what we did with RD is instead of taking dj minus 2, we took dj. But by the time we get to jd, since this sum is positive, dj has to be at least 3. So this sum will be bigger. Okay? And furthermore, as we pick out degree vertices, as this sum is going to change, the sum of d minus 2, the worst case is if you pick out the highest degree vertex. Okay? So until we picked out total degree at least RD, it will still be positive, because the worst case would be to pick out the high degree guys, and we still have this sum left. JD would be the same, and we'd still have a high value, right? But then, once we picked all the high degree guys, it'll go negative. So once we pick degree RD, we would expect it to be negative. Okay? And because we'll pick the high degree vertices, they're more likely to be picked to probably pick a vertex that's proportional to its degree. So you can think about the process, basically what it's really doing is it should be basically picking high degree vertices. So here's the theorem then. The theorem is that we need to look at RD, and we need to compare RD with M. Okay? And if RD is a constant fraction times m, then there will be a giant component. And if RD goes to 0, is little o of m, then there won't be a giant component. Okay? So we've sort of seen why we look at RD. That's a natural thing to look at. That's how long the process continues on. We want to ask, why are we looking at m instead of n? And why do we only look at well-behaved degree distributions? Okay? So the reason we look at m instead of n, if you look at the graph we're looking at and you suppress all the vertices of degree 2, you get a multigraph with m edges. Okay? And basically, once you've chosen the multigraph, these edges are going down everywhere equally likely. That's not quite true, because if you have a loop, you have to put 2 vertices on the loop to keep it simple. And if you have parallel edges, you have to put 1 vertex in all but one of the edges to keep it simple, to avoid but basically, these vertices are going down anywhere. So basically what's happening is the number of vertices of the graph is the same as the number of edges. The proportion number of vertices of the graph is like the proportion of the number of edges of the hypergraph. So we're really interested in edges of the hypergraph, which is m, and whether or not we're going to grow that proportion before the expected change goes negative. Okay? And as we already said, if we have a random 2 factor, then we don't have a 0, 1 behavior. The probability you have a giant component is strictly between 0 and 1. And that's actually the same if we have just a constant number of vertices. The sum of the vertices of degree, which are not 2, is a constant. Then again, we don't have 0, 1 behavior. So we can't prove the theorem for badly behaved graphs because it's not true, but we do know what happens with badly behaved graphs. So basically, we know what happens everywhere. And I'll stop there. Thanks. So if it exactly equals 0, then RD will be little o of m, right? So it means that there is no giant component. Okay? Sort of related to that question, the point where the threshold here is what happens if RD is little o of n, or little o of m? So let me just actually put this up. See, when RD is little o of m, you'd still think that the size, you should grow until you've seen RD edges, which means you're getting RDN over m vertices. So an interesting question about the threshold is whether this is true even when RD, we proved it when RD is epsilon times m, but it may be true all the time. so if you take any model, then you just figure out what the degree sequence is, and then you can apply this result to that degree sequence. So it basically applies to all those models.